Hello and welcome to Quantitative Reasoning. In this video, we're going to talk about how numbers can be deceiving. This is a good time for me to remind you that now is a great time to stop, go get a calculator, and come back. And also there's a lot of reading in this video, so I'll read it all out loud, but feel free to just skip over the parts where I'm reading if you want to read it by yourself. Let's get started. The government administers polygraph tests, also known as lie detectors, to new applicants for sensitive security jobs. The polygraph tests are reputed to be 90% accurate. That is, they supposedly catch 90% of the people who lie during their interviews and validate 90% of the people who are truthful. Most people therefore guess that only 10% of the people who fail their polygraph test have been falsely identified as lying. In fact, the actual percentage of false accusations can be much higher, more than 90% in some cases. How can this be? We'll discuss the answer soon, but the moral of this story should be clear. Numbers may not lie, but they can be deceiving depending on how we interpret them. So in this unit, we're going to discuss several common ways in which numbers can be deceiving. And the way that the data is presented makes a big difference here. So a very common place that we see, percentages that look really good but might not be as good as they seem would be, drug companies. They want to promote their new drug. They want to show how effective it is. So they cherry pick which elements of the data they show so that it looks like, oh, wow, that's really effective. Look at that go. When in fact, you want to look at all of the numbers and make the judgment for yourself. Speaking of pharmaceutical companies, let's look at our first example. Suppose a pharmaceutical company creates a new treatment for acne. To decide whether the new treatment is better than an older treatment, the company gives the old treatment to 90 patients and the new treatment to 110 patients. Here are some of the key facts or the key findings. Among patients with mild acne, 10 received the old treatment, and of those 10, 2 were cured. So that gives us a cure rate of 2 over 10, which would be 20%. 90 received the new treatment and 30 were cured. So that would be 30 over 90, which would be a cure rate of 33%. Okay, new treatment looks good, right? Let's keep reading. Among patients with severe acne, 80 received the old treatment and 40 of those were cured. So that's 40 over 80, which would be 50% cure rate. 20 received the new treatment and 12 were cured. So 12 out of 20 would be 60% cure rate. Okay, those look good, right? The cure rates were better for both. Here's the information expressed in it's called a two-way table. It tells us 2 different pieces of information. Actually, this one's 3 because we have a third dimension here with the different types of acne. So is it fair for that company to claim its new treatment is better than the old treatment? They looked at each case separately, but what if we look at the cases together? That is the total number who were cured. So we're going to look at the total number who were cured with the old treatment. And the number cured with the old treatment would be 2 and 40, so 2 plus 40, or 42. The total who were given the old, do you remember what that number was? Well, if you forgot, it would just be 2 plus 8 plus 40 plus 40, but it was 90. So with the old, we would have 42 out of 90, which looks like just under a half at 46.7%. And if you're not sure where I got this from, you can divide and multiply by 100 to convert it to a percent. If you just do 42 divided by 90, you're going to end up with the decimal 0.46 blah, blah, blah. Okay, how about cured with the new? Let's look at just the straight up percentage of those cured with the new. So we have cured 30 plus 12. And that would add up to also 42. Interesting. So they both have the same numerator. They both have the same comparison value. But how many were there in that new group? Do you remember? There were 110, right? 30, 60 is 90. That's 20. There was a total of 110. So I know this is already going to be a smaller percentage because it's the same numerator with a bigger denominator. This gives us 38.2%. So isn't that crazy? Even though we look at each one separately, we get higher percents, but when you look at everything in total, you end up with smaller percents. So it looks like maybe the old treatment is a little bit more effective than the new treatment overall. Now, why would this pharmaceutical company want to release this data instead of this? Well, because again, they're trying to make this new product look like it's more effective. So they're going to find they didn't lie, right? You can do the calculations and get those numbers. but we do see that the old is more effective. Now, what's one thing that really jumped out at me was the difference in the numbers of who received the old treatment and who received the new. Only 10 people received the old treatment who had mild acne, whereas 90 who had mild acne received the new treatment. So I thought that was a little bit suspicious. And then we see with the severe acne, 80 people received the old treatment and 20 received the new. So to me, those numbers are way off, and the company should have had them more, right, maybe 45 and 45 and 55 and 55, where the numbers are a little bit closer together. So I didn't like that the pharmaceutical company very much skewed who received which treatment based on the severity of their acne. Let's look at another example. This table here gives the shooting performance of two players in the two halves of a basketball game. Kevin had a higher shooting percentage in both the first half, that would be 40% to 25%. Do you remember where those numbers come from, where this 40% came from? The baskets over the attempts, right? So 4 over 10. Whereas Kobe had 1 over 4, so that would be 40% compared to 25%. And Kevin had a higher percent in the second half, 75%, 3 out of 4, versus 7 out of 10, or 70%. Does this mean that Kevin had the better shooting percentage for the entire game? Well, if you look at the stats at the end of the game, it's not, potentially won't break it down by half. It's going to give you the total percents. So let's start with our total for Kevin. And our total for Kevin would be, we have how many baskets? We have 4 baskets and 3 baskets. So 4 plus 3 is the numerator, out of 10 plus 4, right? Because it's going to be baskets over attempts, 10 plus 4. So this would be 7 out of 14. So for the whole game, Kevin had a 50% shooting average. How about Kobe? May he rest in peace. At this recording, we're just at the year anniversary of his passing. Very sad. We have baskets is 1 plus 7 in the numerator. Attempts would be 4 plus 10 in the denominator. This would be 8 out of 14. So without converting to a percent, I already know this is going to be higher because look at the reference values. They're both 14. They both had 14 attempts, and this would be 57.1%. So actually in the entire game, Kobe had a better shooting percentage. Kind of crazy that it shows that Kevin had a better shooting percentage in either half, but overall, Kobe had the better shooting percentage. So again, nobody's wrong here. You can use either one to prove your point. So if you're trying to prove that Kevin's a better player, you're going to use the information based on the halves. If you're going to prove that Kobe's a better player, you're going to use the information from the total game, because either way we look at this, we see one person had a better average than the other. Let's look at another example. In the early 1970s, a medical study in England involved many adult residents from a district called, what I'm going to guess is Wickham, but England, they have a lot of weird words and things that I don't know. So we're going to assume it's Wickham. I'm really sorry if that's not how it's pronounced. 20 years later, a follow-up study looked at the survival rates of the people from the original study. The follow-up study found the following surprising results. Among the adults who smoked, only 24% died during the 20 years since the original study. Meanwhile, among the adults who did not smoke, 31% died during the 20 years since the original study. Do these data suggest that smoking can make you live longer? What do you think? Well, while the data doesn't lie, what information is missing? We want to think about what's missing. What don't we know? Well, one crucial thing we're missing is the ages of these people, right? If the average age of the smoking adults was 20 and the average age of those who did not smoke was 70, then of course it makes sense that there were more people who were 70 and then 20 years later would have been 90, that only a certain percent of them were still alive. But also other risk factors. Maybe all the adults who did not smoke were diabetic or something that would put them at a greater, maybe they were obese, whereas the adults who smoked were not. There's a lot of information missing. And in fact, the big thing was the age. When researchers went back to try to figure this out, they realized that the non-smokers in this group were on average older than those who did smoke. So you can't really make that comparison and say, well, smoking is going to make you live longer. And in fact, other research suggests just the opposite. When a study was done who compared 55-year-olds, so there we're holding the age constant, 55-year-old smokers versus 55-year-old non-smokers, they did find that more non-smokers made it to 75 than their smoking counterparts. So in that case, if you were 55 and smoking, you were less likely to make it to the age of 75 than if you were a non-smoker. So again, just another way that these data really can be skewed based on pieces of information that are missing or based on the way we interpret the results. Okay, so this is kind of a sensitive subject, and I'm really sorry if you or a loved one has ever had to go through with this, but this is the medical examples are really, really important to try to understand and to help us make sense of what happens if we receive something we don't want to hear. So let's consider a study in which mammograms are given to 10,000 women with breast tumors. So they already have a tumor. Assuming that 1% of the tumors are malignant, that's the bad kind, that's the cancerous kind. So benign means there's no cancer, malignant means there is cancer. So assuming 1% of the tumors are malignant, that means that 100 of the women actually have cancer. The remaining 9,900 women have benign tumors. Table 3.7, which we see on the next page, will summarize the mammogram results, but we want to note the following here. The mammogram screening correctly identifies 85% of the 100 malignant tumors as malignant. So 85% that showed there was malignant were malignant. That is, it gives a positive result, in this case positive is bad, for 85 of the malignant tumors. These cases are called true positives. And the other 15 malignant cases, the result is negative, even though these women actually have cancer. So if you actually are positive, but your test result says negative, that's called a false negative. The mammogram screening correctly identifies 85% of the 9,900 benign tumors as benign. That is, it gives negative results for 8,415 of the benign tumors. These are called true negatives. That means you got a negative result and you were in fact negative. The rest of the 9,900 women with the benign tumors got positive results. So you can see how big that number is. 1,485 women who had benign tumors got a positive test result with the mammogram. That's called a false positive. So overall, the mammogram screening gives positive results to 85 women who actually have cancer and to 1,485 who do not have cancer. The total number of positives is 85 plus 1,485, or 1,570. Because only 85 of these are true positives and the rest are false positives, the percentage of actual cancers among the positive tests is 85, the positive, over all the positive tests, which is 5.4%. So therefore, when you or your patient's mammogram comes back positive, should you totally freak out? Only a little bit. You can be assured that there is a chance you got a false positive. So you want to just keep that in mind always. That's why they always say, go for a second opinion. Okay, so here we see this table again. This is again a two-way table. We see positive and positive. So there's the true positives. Negative and negative. There's the true negatives. These are kind of the not great ones, is when you get the false positive or the false negative. So based on this table, what is the percentage of women with negative test results? So we're looking at our negative test results here, who actually have cancer. So what percent are false positives? So we know our reference value is all the women who received a negative test result. How many women received a negative test result? 8,430. How many should not have received a negative? That would be right here, the 15. So it's 15 divided by 8,430. And if we do that and multiply by 100, this ends up being a teeny tiny little decimal. We end up with 0.18%. So just under 0.2%. That means just under 2 in 1,000. It's a really small amount. So you can feel fairly confident that if you get a negative, that it is a true negative. But if you are suspicious, always go for a second opinion. So the good news is that if you get a negative, it's way more likely than not, 1,998 times out of 2,000 times, it's accurate. So that's the good news about that, is that the false negatives are very unlikely. Okay, so let's go back to that introduction from the beginning, the polygraph tests. We're going to kind of relate this to something else, which is a drug test. So going back to this, the 90% accurate polygraph test can actually lead to a surprising number of false accusations. And you're kind of getting a sense of how these false accusations could come up, how these percents could be, even though it's 90% accurate, quote unquote. The explanation is very similar to that found in the case of mammograms. Suppose the government gives polygraph tests to 1,000 applicants for sensitive security jobs. Further, suppose that 990 of these 1,000 people tell the truth throughout their polygraph interview. So that indicates to us that only 10 people are lying. For a test that is 90% accurate, we will find the following results. Of the 10 people who lie, the polygraph correctly identifies 90%, meaning 9 of them will fail, and they are correctly identified as liars, but that one will pass, that one who says, oh, I know how to cheat the system. Maybe they're the ones who pass, I don't know. But of the 990 people who tell the truth, the polygraph correctly identifies 90%, which would be 891 of them, but that also means that 99 people will fail the test, even though they were in fact telling the truth. So that seems very unfair, doesn't it? So what do we see here? The total number of people who fail the test. Here's fail the test, but they should have failed the test. Here are people who fail the test, but they should not have failed the test. There were only 9 actual liars in the people who actually had a failing test, which means 92% of the people who failed the test were in fact telling the truth. All of a sudden, that 90% doesn't seem so good, does it? Even if it's 90% accurate, of the people who fail, 92% shouldn't have been there, right? They shouldn't have been accused of lying. So we, again, have to be very careful about how we interpret our data. And here's this is going to be expressed as this is called a probability tree. This would be another way. We saw the two-way table. Now we see a probability tree, which we can see here just to see that data again. Okay, we're going to take this and apply it to PEDs, which are performance-enhancing drugs. Hypothetically, all athletes participating in a regional high school track and field championship must provide a urine sample for a drug test. Those who test positive for drugs are eliminated from the meet and suspended from competition for the following year. Studies show that at the laboratory selected, the drug tests are 95% accurate. So that's pretty good, right? Assume 4% of the athletes actually use the drugs. What fraction of the athletes who fail the test are falsely accused and therefore suspended without cause? Okay, so let's break this down similar to what we saw in the previous slide. We have all of the athletes. And we're just, for the sake of interpreting this easier, we're going to say that there are 1,000 of them. It doesn't give us this, but we're just to make it very clear. Okay, so what do we know? We know that 4% of them actually use drugs. So we're going to split this up into non-drug users and drug users. And how many in each category? 4%. So 4% of 1,000 would be 0.04 times 1,000, which would be 40. So there's 40 who actually use drugs. For the non-drug users, this would be 0.96 times 1,000, which would be 960. So 960 non-drug users, 40 drug users. This says that it's 95% accurate, okay? So it's 95% accurate, which means they get a negative, which they should get because they were not using drugs. This would be 0.95 times 960, right? 95% of 960 would give us 912. So 912 of the athletes are non-drug users and they got a negative result. So they're good to go. Yay for them. What about those who are also non-drug users but get that positive result? There's 2 ways we can find this number. We know that whatever this is plus this have to add up to 960. So we know that this number has to be 48. Or we could say, well, that means 5%, right? If 95% got the negative, 5% got a positive of the 960, and if you multiply 0.05 by 960, you'll end up with 48. Okay, let's talk about the bad ones, the drug users. Let's start with our positive here. So this is what should happen. You're doing drugs and you get a positive drug test result. So how would we calculate that? That's going to be 95% of those 40, and 95% of 40 is 38. So 38 of the drug users will get caught. They get a positive, they were using drugs. Bye guys, won't even see you next year. What about these lucky few? Well, I don't know if you're lucky, you shouldn't be using drugs. But the people who were using drugs and got a negative, how can we figure this out? We could either say, well, I know that this plus this need to add up to 40, so it's probably 2. Or we can say 5% of those using drugs got a negative result, and that would be 5% of 40, which is 2. Okay, so this is our table. This is all the data that we were given here with our hypothetical 1,000 athletes. What are we looking for? What fraction of athletes who fail the test? So there's our reference value there. Those who fail. And what does failing mean in this case? That means they got a positive. So failing the test means you got a positive, right? Your blood showed, or your urine in this case showed that you did in fact, well, indicates that you used drugs. Okay, so what fraction? Were falsely accused. What is falsely accused? That means they got the positive, but they weren't doing the crime. How many was that? That was 48. So 48 of these, this would be, this is a false positive. So let's set this up. So there's 48 over how many positives were there? There were 48 positives plus 38 positives, giving us a grand total of about 56%. So all of a sudden, that really doesn't seem fair. 56% of those people who had a positive result were not actually using drugs. That's why, again, we want to be really careful. We don't want to suspend them for a whole year when they weren't doing anything wrong. We need to somehow take this information and figure out another way that we can test these athletes to see if they really should be suspended or not. These have been examples of just looking at how we can skew numbers to justify whatever we need to justify with these numbers. Thank you for stopping by.